Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to talk about Euler's method and Heun's method. So we're going to look at what an initial value problem is, we'll review that, then we'll look at Euler's method, we'll improve it using Heun's method, and of course this will lead to Dorman-Prince and Runge-Kutta methods in the next lecture, and we will also be looking at multi-step methods. So by the end of this lab, you will be able to understand how to approximate a first-order initial value problem using Euler's method. You will also understand the limitations of Euler's method. You will be able to therefore take the ideas from the trapezoidal rule for integration and improve Euler's method, yielding Heun's method. So, given an initial value problem, the derivative is defined as a function of both time and position, and given an initial value at some time t0, we would like to see how this function behaves at some point in the future. We want to approximate the function in the future. So now the first thing you have to ask yourself is, this is very specific. We are having the derivative as a function of both time and position. Is this always true? Is it always possible that you can do this? Well, for example, let's take a look at this ODE. This ODE, defined in terms of cubics of the derivative plus sine of the function of sine of y, cannot be written in that form. Well, fortunately, the implicit function theorem says yes, this is almost always the case. And that's actually quite nice. Now, you may end up using sine or truncated approximations similar to Taylor series, but you can write it in this form. So, therefore, what does this formula mean? Well, this formula means that if at any point t star y star, if the solution is passing through that point, it must pass through that point with this derivative. And we can just plug the two values, t star y star, into that point, and we can determine what the slope of the function is at that point. For example, we have the following ODE. The derivative is negative t times y plus t minus cos of y. And let's say, for example, at the point 1, 2, we can then substitute both t equals 1, y is equal to 2 into that equation, and we know that at that point, therefore, the slope is approximately 1.41 and change. We could, in fact, pick a few hundred points and determine the slope at each of those points. And this is exactly what this type of plot does. Here we have a point, we plug in both the t value and the y value, and that gives us a slope, and then we draw a line with that slope. Now, this sort of gives us the idea that the solution to this differential equation, well, if we're up here, it will increase. However, after a while, it will decrease and it appears to level off. On the other hand, if we're down here, the slope of the function is going to be positive, and it appears as if we will carry on. Again, it seems as if there's a limiting or an asymptote at that point. So in fact, we can take three initial conditions, y at 0 is equal to -1, 0, and 1, and we can watch the propagation of the solution. And again, as it clearly depends on the initial value. Now, the reason I chose that particular ordinary differential equation is because it has no explicit solution. However, let's see an example where we do actually have a solution. Here the derivative is y minus 1 all squared times t minus 1 all squared. And again, plotting the slopes at various points gives us this plot. If we're above this apparent asymptote, we seem to go off to positive infinity. If we're below, we seem to approach that asymptote. And in fact, we know that y is equal to 1 is one of those solutions. If you just pick y is equal to 1, the slope is 0, and the function y equals 1 does have slope 0. So that is in fact a solution. There's another solution that's a little bit more complex. T cubed minus 3t squared plus 3t all over t cubed minus 3t squared plus 3t plus 3. Now, we can plot that in, And if you wanted to, you could even take this rational polynomial, substitute into here, and calculate the derivative, and it would in fact be equal. So we can do so. That's a derivative using the rules you learned in first year calculus. At the same time, if you substitute the original into here and then expand it out, everything cancels. Everything except for 3 cubed is equal to 9. Now, we see that at y at 1 equals 1. This value is true, that value is true. The slope at this point should be 16. Okay, that's what the formula claims. However, if we substitute that into our derivative, we also get a slope of 1. Now, let's try to figure out how we're going to actually approximate these. We've looked at a few solutions to initial value problems, but now let's try to actually approximate numerically. Now, we have some initial condition. We are saying that we know the state of the system at t0 and the state of the system is y0. We also know how it propagates into the future by the ordinary differential equation. Suppose we want to approximate the value of the function at some point in the future, t plus h. Well, we can use Taylor series again. So substituting Taylor series here, we have that the function at t0 plus h is equal to the function at t0, a value we know, plus the derivative at t0 times h, plus an order h squared term. And tau is some value between t0 and t0 plus h. Now we can replace that initial condition, and so now we have that this value is equal to the initial value plus the slope times h plus the second derivative times h squared all over 2. We also know the derivative from the ordinary differential equation. We can substitute that in, and we know what the derivative at time t0 is. It's just this function evaluated at t0, y0. So therefore, we have that the value of the function at some point in the future is equal to the value of the function plus the slope at that point times h, we're stepping forward a distance h, plus an error term that is order h squared. So therefore we can approximate the next point. The next point is the first two terms, and the error term depends on the second derivative and h squared. Now, using our example, we know what the actual solution is, and so let's compare the actual solution with what we estimate. So we can implement both the right-hand side as a function in MATLAB, but we can also implement the solution. The solution is exactly what we previously found. And again, notice I'm using the dot operator everywhere so that our functions work on both scalars and vectors. So now I can approximate. There's my initial condition. At time t0, the value is 0. Okay, so there's 0. And 0.1, h is equal to 0.1 times the slope. And so we get ours as our approximation, 0.1. Now if we calculate the actual value at that point, well, we can just substitute 0.1 into the solution, and we get a value of 0.082 and change. Not close, about 10% relative error, but not terrible. Actually worse than 10%. So again, the absolute error is 0.017. Now, let's have h now. Okay, so remember that the error term was h squared. That suggests that if we have h, the error should drop by a factor of 4. So let's try that again. Let's approximate y at 0.05. All right, so we plug it in, 0.05, well, we're following the same slope. The actual value is 0.045, and the error has dropped significantly. In fact, if we compare the error with the previous error, 17 divided by 4 is 0.017 divided by 4 is approximately 0.046, approximately. So it does appear that the error has dropped by a factor of 4. And even if you look at the solution, you will see that locally, the quadratic term is the component that is most significant in the solution going away from the slope at this point. And so we would expect a more significant error out at time t equals 0.1 than at 0.05. Now, unfortunately, we have an issue here because our goal is to actually approximate the solution at 0.1. Well, we can get a better solution here, but that still doesn't give us a better approximation at this point here. So how are we going to do that? Well, we are now at this point here, 0.05, 0.05, slope 1, and could we not take this point here, figure out what the slope is here, and having found that slope, it's going to be a little bit more shallow, let's follow that slope out a distance of 0.05. Well, if we do so, we can calculate the slope at that point. There is our value, 0.05, plus our h value, 0.05, times the slope at that point. And now we're getting a slightly better approximation. Remember, the previous approximation was 0.1. Now our approximation is 0.09. We could even repeat this. We could, for example, take this point, determine the slope at that point, and then going out a distance 0.05, approximate the solution at 0.15. And again, you can see that our solution is sort of shadowing the actual solution in red. So this is the actual solution, and we're sort of following it, overshooting, but we're following it. Now, notice what happens though. If we have to reduce the size of h, we also have to do more work. So if we have h is equal to 0.1, we may require a number of steps. If we reduce h by half, then we would need twice as many steps. That would reduce the error, but we have to do more work. If we divide h by 10, once again, we have to do 10 times as many steps, all of which to approximate the same value. Also, we have another issue. I'm using the exact value at the initial value point here, but here I'm using an approximate point to approximate a next point. And at this point we're using an approximation to approximate another point, but that used an approximation. So how good does Euler's method really work after a while? Well, we're going to look at that a little bit later when we do the error analysis, but fortunately it isn't actually all that bad. So that's going to be a little bit interesting. We'll get into that in a bit. But now let's just take a look at solving an initial value problem. Suppose we have our initial value problem and we want to approximate the solution all the way up to some point t final. We could use h is equal to t final minus t naught, but again, we're not going to have significant accuracy. So instead, what we're going to do is we're going to divide the interval t naught to t final into n points, and then we will repeat Euler's method n minus 1 times on that interval. All right, so for example, here we have our initial point, y at 0 is equal to 0. We want to approximate y at 1. So let's break n is equal to 11, we'll break the interval up into 10 points, and we will apply Euler's method 10 times. So right here, we're at the start, we calculate the slope, we follow the slope out a distance 0.1, and we get an approximation. Now we can approximate the slope at this point, follow that out a distance 0.1, and we get the next approximation. We repeat the process again. And at this point, we can do the same. Calculate the slope right there, and follow that slope out a distance 0.1. repeating it again and again and again, every time calculating the slope at the point, following that slope out a distance 0.1, and finally we have an approximation of the function at 1.0. Not an amazingly accurate approximation. Our error here is reasonably significant, around 15 to 20% relative error. However, it does at least appear to be tracking the solution. So it's not diverging from the solution. So what you're going to do is you're now going to implement exactly this method. You're going to implement Euler's method to try to approximate these. The first parameter is a function, and it'll be a function handle. The second parameter is a range. It's a pair or a row vector of two values giving the initial value and the final value in time. We're also going to have an initial condition and the number of points into which we will break the interval up into. Now, we're going to return two vectors. The first vector that's returned is t out. It's a row vector with n equally spaced points, and from t naught to t final, and y naught is going to be a row vector of n points where the first point is the initial value and the kth point approximates the solution at the kth value of t out, at least for values of k from 2 to n. Now, this function will first of all determine the value of h. Then it's going to assign using lin space, n equally spaced points between t naught and t final. Y out might as well just be assigned a row vector of zeros of size n. We can then initialize the first value to be y naught. Then going from k from 1 to n minus 1, using the function to approximate the slope, calculate the slope at that point, and then having calculated the slope at this point, approximate the next point by using Euler's method. For example, consider we have this initial value problem. If we want to approximate the solution on the interval 0, 1 with 11 points, we can plug it in, we get our 11 equally spaced points, and then we get our approximations at each of those points, and therefore an approximation of the solution at 1 is 0.2907. So again, there's our solution. Now, how can we tell in MATLAB how good the solution is, especially if we do not have the exact solution? Well, fortunately, the format here is almost identical to MATLAB's built-in ODE solver, ODE 4.5. So here, the first three arguments are identical. That's why I gave you the signature for Euler's method that I did. The only difference is you don't give the number of points to ODE 4.5. ODE 4.5 uses an adaptive technique called Dorman-Prince, which we will be seeing next lab. However, this is, for our purposes, probably a good solution or approximation of the solution. Now, if we use 21 points or divide h by 2, notice that the error appears to drop. In fact, the error sort of appears to drop by half. Okay, so here's a different solution, or here's our different initial value problem. At time 0, we have a value of 1. We can plug this into Euler's method, and again, we get a solution, and the solution, or the approximation of y at 1 is 1.8543. And now, once again, we use ODE 4.5 to approximate the actual solution very closely, and we see how well Euler's method does. This time, Euler's method is lagging below. If we increase the number of points by a factor of 10, so now we're using 101 points for Euler's method, we see that it's tracking much more closely. The approximation is better, but we had to do more work. Now, we saw that Euler's method was order h squared, but again, only the first approximate point is exact. Everything else is an approximation using an approximation and an approximation. So what is the actual error? Well, the total error is simply going to be the error of applying Euler's method here, the error of applying Euler's method here, the error applying Euler's method here, and so on and so forth. And if we go back to the Taylor series expansion, we see that this is the sum of the errors on our interval. All right, if that's the sum of our errors, here tau k is some point on this interval, on each of the intervals. And we can simplify this by extracting out an h over 2, and now we have this sum. We have a sum of the second derivative times h. Now what does that look a lot like? I'm sampling the function at points tk, multiplying each of them by h, which is the width of the interval. This sounds a lot like a Riemann sum. And so that's exactly what you learned in first year. You saw that an integral can be approximated by a Riemann sum. The smaller the value of h is, the better the approximation. And so essentially, this component here is simply approximating an integral. So what we have here is that the error is approximately h over 2 times this integral. Now, the integral here, that's a fixed value, right? We already know that a solution exists, at least for most problems. Again, the existence of solutions is something you look at in your actual course. But assuming a solution exists, the second derivative exists. If the second derivative exists, this integral exists, and so this is a constant. So this says that the error of Euler's method over multiple steps is not order h squared, but order h. So by repeatedly applying Euler's method multiple times, the error drops from order h squared to order h. So you're going to use Euler's method. You're going to see that having the value of h will have the error at the last point. You will also see that reducing h by a factor of 10 will reduce the error by a factor of 10. This is unfortunately very inefficient. And so we're going to first see Heun's method, which is better. And then in the next lab, we will look at Runge-Kutta and Dorman-Prince. But how are we going to go about improving Euler's method? Suppose that we have some function here that we want to approximate the integral of. I could approximate the integral by just taking the value of the function here and multiplying by the width of the interval. Not a very good approximation. Instead, what we do is we can use the trapezoid rule. The trapezoidal rule says calculate the area of this trapezoid, and that is a better approximation. Not a great approximation, but a better approximation. And so it's just the average of the two values, the values of the function at each of the points times the width of the interval. That's the trapezoidal rule. Now, what are we doing when we're solving an initial value problem? We have the derivative. We know what the state is at that derivative. So essentially, what we're doing is we're integrating the derivative from our initial point t0 to t0 plus h, and that is our function f here. Now, we know that this integral, a solution exists, so just by using the fundamental theorem of calculus, we have that this is equal to the value of the function at t0 plus h minus the value of the function at t0. Bringing this term over to the other side, we now have that the value of the function in the future is equal to this value here plus an integral term. So therefore, the derivative, we have, therefore one approximation of this integral is simply calculating the slope at the initial point and multiplying by the width of the interval h. Somewhat suboptimal, because we're only using the value, we're doing an integral, but we're only using information at one point. So what we'd really like to do is calculate or know what the slope is over here at t0 plus h. But we don't know what the slope is there because we are only looking at t0. So therefore, we only have one slope here at t0, y0. However, we can actually take a step forward and find an approximation of the value of the solution at t0 plus h, and that's just y0 plus h times k1, k1 being the slope at this initial point. So great. Sorry about that. Now we have an approximation of the solution at the second point. So we have the slope at the initial point, the slope at the second point, which is just the function evaluated at t0 plus h, y0 plus h times k1. This we can find, therefore we can find that. And so therefore let's take the average of those two. Essentially we are applying the trapezoidal rule. K2 isn't perfect because K2 is only an approximation, because this point here is only an approximation, but it's better than just using the initial point or the initial slope K1. So we'll use the average of the two and follow that out. So essentially what we're doing is we're going out halfway. Having gone out halfway, or no, sorry, we go out all the way. At that point, we calculate the slope K2. We calculate the slope at that point. And again, it's just evaluating this formula. We take the average of those two slopes, and we follow the average of those two slopes out a distance h. Notice we get a much better approximation. Thus, you're going to write a second function, Heun, and that's going to have the identical signature as Euler, where you will again determine the value of h. You will then assign t out and y out the appropriate vectors as before. The only difference now is you will find k1 and k2, and then your approximation will be the average of those two times h plus the previous value. So, for example, consider our initial value problem again. Approximating it with 11 points gives us an approximation at y at 1 is equal to 0.2508. Let's see how that looks. Actually, that's pretty good. Heun's method seems to be doing reasonably well. Here we have another initial value problem. Again, substituting it in, we get the approximate value at 1 is 1.9362. Again, a very good approximation, and if we compare it with Euler's method, significantly better. So it seems that Heun's method is significantly better than Euler's method. In fact, even if we reduce h by 4, it's still not as good. Here we have Euler's method approximating with a h equals 0.1. The smaller dots are Euler's method with h is equal to 0.025. So we've divided h by 2. However, Heun's method is still better. It's significantly better. In fact, if you compare the difference between the approximation of Heun's method and the approximation with Euler's method with 4 times as many points, it's still significantly better. The absolute error in this example is reduced by a factor of 3. Now, to be fair, we actually should be counting function evaluations, not just how many points, because Euler's method uses one function evaluation per point or per interval. Heun's method uses 2. But still, with half as many function evaluations, we're still getting a better approximation. So Heun's method still comes out ahead. Now, as far as the error analysis is concerned, without proof, I'm just simply going to state that the error for Heun's method is order h cubed. If you want to go look at my online textbook for Heun's method, there you will see the full derivation of the error. However, it is order h squared. But again, as before, with Euler's method, we were approximating a point using an approximation and so on. And so just like Euler's method, the rate of error, the error term becomes order h squared when you repeatedly apply Heun's method multiple times. So in summary, we've looked at both Euler's method and Heun's method for approximating first-order initial value problems. Euler's method is direct. It uses the Taylor series approximation. Heun's method uses the ideas from the trapezoidal rule for integration, and that improves on Euler's method. Heun's method requires twice as many function evaluations as Heun's method does per step. Heun's method requires twice as many function evaluations per step as does Euler's method, but it's still significantly more accurate. Next week, we're going to see Runcuta, which is order h to the fifth, and then we will see Dorman-Prinz, an adaptive technique. Thank you very much. Good luck with your lab, and have a good day. Cheers.